Okay, so the next example is that of a compressor. Okay, and just like before, we'll dissect the problem and pull out the pertinent information. So the substance is R134A. It's going through a compressor, an adiabatic compressor. So right away we know that Q dot in equals Q dot out equals 0. Um, it comes in as a saturated vapor. Now that is meaningful to us, right? What does that mean? So it's coming in, enters the compressor as a saturated vapor. So this is because it's adiabatic. Saturated vapor just means that the quality at the entrance is 1. So it enters as a saturated vapor, meaning the quality is 1. Quality at state 1 is 1. Yeah, all right. So I know T1 is just given to me, negative 24 degrees C. P2, it exits, the refrigerant exits at 800 kPa. And the temperature at the exit is 60 degrees C. And M dot in equals M dot out equals 1.2 kilogram per second. And this is because it's an assumed steady operation. All right. Okay. So the energy balance reduces that again because it's a steady device, which means that the energy content via mass or I'm sorry, the energy input via mass, work, and energy is equal to the energy output via mass, work, and heat. Okay, it's adiabatic, so these are necessarily going to be 0. There is no work output from the device. The idea of a compressor is that we take work input and produce a change in the energy of the fluid. So work out is going to be 0. So this whole thing reduces to so you can see that work dot in is equal to, I got to take m dot theta 1 to the other side, so that gets a negative sign. So m dot theta 2 minus theta 1 is equal to work in. Okay, and then I kind of switched them on you, so hopefully that's not confusing. All right, so it's pretty straightforward to see that this reduces to this. Okay, so now let's expand the thetas. All right, so we get m dot inside the brackets. I get h2 minus h1 plus 1 half v2 squared minus v1 squared, or the change in kinetic energy, plus the change in kinetic energy, or I'm sorry, potential energy. So that's just expanding these theta terms into individual enthalpy, kinetic energy, and potential energy, and then sort of grouping them like this. So you could, it's pretty easy to go from here to here, and I'll leave it to you if, as a exercise, I suppose. Okay, now the change in potential energy across this device is negligible, and by assumption, the change in kinetic energy is negligible. So the changes in kinetic and potential energy are negligible. All right, and this is by assumption. Okay, what I'm saying, and I went over this a little bit in the lecture for the specific to the compressor and turbine devices. The what we're saying here, the change in velocity is not zero, right? But what we're saying is that it's small, very small relative to the change in enthalpies. So it can be assumed to be zero. All right, so this whole thing simplifies. Okay, and the point of the problem, or at least part A of the problem, is to find work in. All right, so m dot is given. H2, I have two intrinsic properties that are hopefully independent. I'll have to find out. And then for state 1, I have two necessarily independent intrinsic properties. So I have everything I need to find H1, H2, and m dot. So H2 is just going to be the enthalpy. The enthalpy at state 2 is the enthalpy as a function of pressure and temperature. I plug that into my calculator, I get this. The enthalpy at state 1 is going to be the enthalpy as a function of temperature and quality. All right, so now I have everything I need. So the power input is 73.2 kilowatts. So if you figure this out, look at the units. I got kilojoules per kilogram times kilojoules per second, or I'm sorry, kilograms per second. The kilograms cancel and I get kilojoules per second equals kilowatts. Okay, so that's part A. Now part B is to ask the volume flow rate of refrigerant at the inlet. And that's just an understanding that the volume flow rate at the inlet is equal to the specific volume at the inlet times the mass flow rate. Okay. And so the specific volume at the inlet, I can take it to be the same, a function of the same variables as I used to calculate the enthalpy at the inlet. So and I plug that into my calculator, I get 0.209. And if you calculated that at the exit, you'd get a different number. That's sort of the upshot there. No, I'm sorry. The specific volume is 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 that, and then I got to multiply. There you go.